Hey y'all, let's cover lesson one. It's an introduction to whole numbers. All right, so the first one says one of the most basic foundations of math is numbers, the language. In math, we use different types of numbers for different things. What are some different types of numbers that you can think of? So I know you're not here, so I'm just gonna choose my favorite number 5, 7, 12. What about negative numbers? There's negative. There's decimals. There's everyone's favorite fractions. That was sarcasm. There's rational numbers. Oh, I didn't realize my hands looks like they're great. Rational numbers. Integers. And we can just start throwing out different things like 3 cubed. It's just numbers. Okay, so we organize these numbers into groups called sets. It's a collection of objects. Okay, so the next one is the first set of numbers that we learn to use are called the natural numbers. And those were 1, 2, 3. When you teach about teaching a child, think about teaching a child numbers. First thing you do is 1, 2, 3, 4, 5, and continues on. So the natural numbers that are represented this way, you don't need to know that, but just to know that you could just write the natural numbers. Start off with 1, 2, 3, 4, 5, and then they just keep going on and on forever. No fractions, no decimals, no negative numbers, no zeros, just 1 and on. Okay. What do we use this set of numbers for? We'll use it for counting. Okay. By adding one number to this set, we create the whole numbers. These are used to answer the question, how many? So if we're counting, we're using the natural numbers 1 through on and forever and ever. But for how many, we could answer 1, 10, a million, or 0. So the whole numbers start at 0. Again, no fractions, no decimals, just whole numbers and forever and ever, and no negative numbers. We can use a number line to visualize different sets of numbers. Larger numbers are to the right. Smaller numbers are to the left. Okay. Graphing a number on a number line means that we should indicate where the number is by drawing a dot there. The whole numbers have a natural order, and we use symbols to illustrate the relationship between these two numbers. So if A is a number and B is a number, they're both whole numbers. So anywhere between 0 and infinity, A lies to the left. Maybe I just said A lies to the left of B, then we say A is blank. Oh, okay. So I get to choose which one I choose there. So if A lies to the left of B, then we say A, I'm going to write it the way I would write it, is less than. I'm going to show you the symbol. The symbol is for less than is this. A is less than B is how I would write that. Okay. If A and B are whole numbers on the number line, so that A lies to the right of B, then we say that A is larger than or greater than B, and we write that A is greater than B. All right. When we compare two numbers, we have 3 options. We have A is less than B, A is greater than B, or A is equal to B. We have 3 options. A is less than B, A is greater than B, and A is equal to B. Those are our three options. There are also other comparison symbols that illustrate slightly different relationships to where you can have more than one of these at the same time. So A can be less than or equal to B, so where it's less than and or equal to, or you could have A is greater than or equal to B. Again, these are just numbers that we're choosing variables just to represent them so we can have this conversation. Okay. If you find while you're taking notes through this, you have any questions, please write it on a separate sheet of paper and then email it to me. Email me what your questions are at the end so that we can either get together or maybe I can answer you in an email. Okay. I do not want to leave you hanging. All right. Let's talk about rounding. I have to go over rounding in every single one of my classes. I don't care if I'm teaching college algebra or this class. Everyone still struggles with rounding, and hopefully we can put it into that. Not with this section that I'm going through right now, but before we're done with this lecture, hopefully. All right, rounding. In some situations, we require numbers that are less precise, so they're not exact. Especially in science classes, you'll see that more so than math. For example, suppose a store owner needs about 87 boxes of 10 penny nails, but they can only be ordered in cartons containing 10 boxes. How many should he order? Well, they can only be ordered in 10. He has 87 that he actually needs. So who's closer? Should we go up or should we go down? So, how can we do that? Well, we would have to divide this by 10 because there's 87. Yeah, he needs 87. Okay. So if he needs 87, we're going to have to find out how many cartons. They're boxes of 10 penny nails. So there's 10 per one. And we have 87 that we need. Well, we need at least 8 cartons, right? Because that's 80. But we're going to round this too. One, we're going to round this for normal reasons because you can't, even if this was 81, this isn't even a great question, because even if this was 81, you're going to need 9 boxes. You're going to need 9 boxes because 8 boxes is only going to give you 80. 9 boxes will give you 90. You wouldn't have enough if you only got 8 boxes. So even for this one, using this, I can explain the rounding portion of stuff, but even knowing that it's 1 over how much you have for this entire class and your next one, this is a logical thing you're going to have to understand. If you go to the store and you need 81 of something and it comes in boxes of 10, you're going to need 9 boxes, even if you're going to have 9 left over. Okay. So how many should he order? Whether it's 87 or 81, he's going to need 9 boxes or 9 cartons. Sorry, 9 cartons. A little too excited there. How did you decide this? Why is this the best answer? Well, I think I explained that. 8 cartons isn't enough. Need 9 to have 87. Okay. What if the boxes can only be ordered in cartons containing 100 boxes? How many should he order? Well, that's pretty simple. 1. I mean, if it already has 100 in it, we only needed 87. So that's going to have to be one box. So 1 carton. So what if boxes can be ordered in cartons containing 100? So we need 1 carton with 100 boxes because he originally needed 87 and you can't order less than that. So we'll just have to take the 100 boxes. On the other hand, the store owner estimates that he will need 230 bags of peat moss for his garden section It is easiest to order these bags in multiples of 100. How many should he order? So he's estimating he needs 230 bags. And he's a store owner. Do you go and buy 200 and potentially have to get either run out and go get, more on an individual basis, or not have just run out, lose those 30 bags of opportunity of selling? Or do you buy 300 because they're in multiples of 100? So it's either 200 or 300. And you buy 300 bags of peat moss and you have 70 or more or less, right around 70 bags left over. How many should he order? And why? I'd be curious to know your reasoning. Think of it as a business owner. As a business owner myself, I'm going to say 200 bags, have the missed opportunity of sales of 30, and then that way I don't have 70 bags left over. So how many should he order? He should order 200 bags. The other reason to think about that, now we have to think about this in logical reasons. These are problem solving skills to actually be able to utilize. But also, if you want to think of this as rounding, this is a good explanation. When I think of rounding, I think, okay, it comes in hundreds, so I'm going to have to round to my 100, period. That is my rounding digit. That is who I'm going to be deciding everything from. Looking at my rounding digit, the one digit just to the right of that, no matter what this number is, the one just to the right of that is always our test digit. So rounding digit and test digit. The test digit, which I'm going to explain this to you again here in just a minute. The test digit, if it is greater than 4, so if the test digit is greater than 4, or some of you might have learned it as if the test digit is greater than or equal to 5, you can use either one of those, just pick one. If that test digit is greater than 4 or greater than or equal to 5, then you would add 1 to your rounding digit. That is not the case, so we add 0 and everything else becomes zeros. You just leave the first digit alone, the rounding digit, and everything else after the rounding digit becomes zeros. If that 3 had been a 5 or greater, that rounding digit would have become a 3. You would have added 1 to it, and you would have bought 300 bags instead of 200. Now let's think about that in the problem solving sense. If you needed, if we got there, we had 250, say he needed 250 bags. Okay, say you needed 250 bags. That would tell me on the rounding aspect of it that I would need to buy 300. Now, it's possible I'm going to sell more than 250 as the store owner. It's possible I'm going to sell less than 250. But then we have to figure out, hey, is $50 worth, is 50 bags worth the potential for having 50 extras? So there's going to be some daily math things that we would need to figure out. We'll do that later down the road when we get to more of a finance conversation. Okay. So let's go down here and talk about what each of these place values are. We've got ones, tens, hundreds, thousands, 10,000, 100,000, million, 10 million, 100 million. Then it goes to the billions, 10 billion, 100 billion, trillion. It just it's infinity. It goes on forever. The rules for rounding. To round a number to a particular place. All right. Mark the place to be rounded. And what I did was I put my RD for rounding digits so that I could do that. So that's what I always do. So 1, you're going to mark the place to be rounded. This is my rounding digit. and I always put RD. Write whatever you want. Make this yours. 2, I'm going to check the next digit to the right. Check the next digit to the right. And this is my test digit. And I call it TD. Okay. While you're checking that next digit to the right, the test digit, if the test digit is 5 or above, and I'm going back up here again, A, if the test digit is 5 or above, increase the rounding. You're going to add 1. I'm not going to say increase. You're going to add 1 to the rounding digit. Add 1, so plus 1 to the rounding digit. Okay. And everything else to the right ends up with zeros. And numbers to right become zeros. Okay. B, if the test digit is 4 or less. So if the test digit is 4 or less, leave the rounding digit and you're going to replace the digits to the right of the rounding digits with zeros. If the test digit is 4 or less, you're going to leave the rounding digit sorry about that, and replace everything else to the right with zeros. Replace everything to the right with zeros. Okay, so now we're going to round the number 9,443 to the nearest 10. I'm going to take 9443 and I'm going to first mark the place to be rounded, and we're going to round it to the 10, which is 1's tens. So this is my rounding digit, which means the 3 is my test digit because it's the one to the right. The first thing I ask myself is 3 5 or above? Nope. So therefore it is you're going to go and be the B, where it is 4 or less. And so all we're going to do is leave it as 9440. The 4 stays the same. The rounding digit stays the same since the test digit is 3. And then the 3 becomes 0 because replace everything to the right with zeros. That's it. This is rounding to the tens place. Okay. Now we're going to round 6,656 to the nearest 100, to the nearest 100. So my rounding digit is the second 6, rounding digit. My test digit is that 5 right there. So A is substantial because it's 5 or above, it's 5. So I'm going to add 1 to my rounding digit. 6, 6, 5, 6 plus 1. Only where the rounding digit is. Okay, so that becomes 6, 7. And now we have to, the numbers to the right become 0. Okay, the reason I do plus 1 instead of increase by 1 is because people, when this becomes a 9, students forget that this becomes 9 plus 1 would become 10 and they get confused, and I don't want that to happen for you. So please just add 1 to your rounding digit whenever your test digit is 5 or greater. All right. One more piece on this. All right, now we're going to round the number 59,741 to the nearest thousand. Oh, there's a cute kitty cat outside. Nearest thousand. So 1, 10, 100, 1,000 is the 9. That's my rounding digit. My test digit is the 7. It is greater than 5. So I'm going to be adding 1 to the 9. So 59,000 plus, I'm just going to get this little trader here for y'all. And that becomes 60,000. So that is rounding the number 59,741 to the nearest thousand. Okay. All right. The symbol, this cute little thingy right here, squiggly lines, means approximately. Approximately. So about. We don't do a lot of approximately in math. We will a little bit here perhaps, but the place you'll use the most approximately's is in science. They're big fans of approximate. Not that I have anything against that. Tables and graphs. So it looks like we've got years here, 1965, 75, 85, 95, and 2005. And during those years, the atmospheric CO2, so the carbon dioxide, was 319 in 1965, 330 in 1975, 344 in 85, 359 in 95, and 378 in 2005. So according to this table, the carbon dioxide values are parts per million varied, derived from in situ air samples collected in Mauna Loa, Hawaii, USA. The above table provides data which measure the blank in the atmosphere. Well, it's CO2. Okay. Gathered in the month of January at the observatory in where? Mauna Loa, Hawaii. Mauna Loa, Hawaii. I'm going to put carbon dioxide here so you know this. Carbon dioxide. All right. We can use different types of graphs to represent data visually. Okay. Here we have a bar graph, and here we have a line graph. So the left graph is a bar graph. The year the measurement was taken is along the horizontal axis. And the height of each bar represents the carbon dioxide content. All right. The graph on the right is a line graph. The year the measurement was taking, the year the measurement was taking is along the, I was looking at this other way, horizontal axis is where the dates are. So the reason for that, and we're going to talk about this a little bit later, just to throw this little snippet of information to you. You've seen X and Y graphs, the Cartesian coordinate system before. The X-axis is always the horizontal one. The Y is always the vertical one. So the X-axis is our independent variable. I know we haven't talked about this, but you've heard this. And in this case, that is always going to be represented if time is available. Time is always independent. Everything is based on time. So this is something nice to keep in your mind for a later information is time is always represented by the independent variable or the x-axis. So the year the measurement was taking is along the horizontal axis, and each measurement is graphed using a dot. Then the dots are connected using a line segments. Okay. Which graph do you think is a better visualization of these data and why? So this is your opinion. Personally, I like the bar graph myself. It just feels more substantial. I guess. I mean, you can, it's easier to see the elevation in the line graph, perhaps. It's your choice. Okay, so that's it for lesson 1. Please message me any questions you have. If you don't have any, get started on your homework. As you find you have any questions in that aspect, hit message the instructor directly from the question that you're asking about and type any questions that you have. If you need to show me your work, you can go in MyOpenMath under the question itself. When you hit message the instructor, hit insert image, and which you can do on your phone, and take a picture and share it through MyOpenMath. You can access MyOpenMath via your phone. In fact, I find a lot of students do that. All right, I will see y'all in the lesson 2, which is coming up next.